It seems like every day AI is getting more and more complex.
It really is.
And, it kind of feels like we're all trying to, grab onto something solid just to get a sense of, what direction things are going.
Right.
But that's why we do this,
Absolutely.
To, really dig in and figure out what's actually important.
Exactly. It's about, going deeper than those headlines.
Right.
And, actually understanding what's happening.
Yeah. And today's project is, well, it's pretty mind-blowing, to be honest.
Oh, yeah.
We're diving into the creation of a virtual reality simulation, and it's like nothing I've ever seen before.
Wow.
It's a digital world, but it's full of these AI agents, and they each have their own special roles and expertise.
It's really impressive.
And you've given me so much to work with.
Oh, good.
Blueprints, development plans, even some philosophical stuff about how they built these digital beings.
Yeah, the source material really dives deep into how they're building this interactive space.
Right.
Where AI agents can learn, work together, and basically function within this set of rules.
Yeah. It's fascinating.
It is.
So our mission today is to unpack all of this.
Okay.
How do they even start building something so complex? How do these AI agents learn and talk to each other? And what's the big idea behind it all?
Those are the big questions.
They are.
For sure.
Let's start with the foundation, the vector space.
Okay.
Now that sounds kind of abstract.
It can be a little bit, yeah.
So break it down for me.
All right, so imagine instead of just listing data, you're placing every single piece of information into a landscape.
Okay.
And that landscape, it has multiple dimensions.
Multidimensional.
Yeah, and each piece of data is placed based on how it relates to all the other data around it.
So it's all about relationships.
Exactly. And to capture those relationships, they use a technique called machine learning embeddings.
Machine learning embeddings.
Yeah, it's a way for the AI to understand the connections between the data.
Got it.
But what's really cool is how they actually visualize this data.
Yeah, I was going to ask about that because the documents talk about all these geometric shapes. Tori vertices, edges, colors.
It's like they're turning this abstract information into a language you can see.
Almost like a code.
Exactly. Each shape, each color.
Yeah.
It represents something specific about the data.
I see. So it's kind of like those charts and graphs we use to understand numbers?
Yeah, but instead of just showing patterns in numbers, they're showing patterns in information.
That's really clever.
It is. And each visual element can have layers and layers of data underneath it.
Wow.
So you have this direct connection between the information and how it looks in the simulation.
Okay, now they also mention these nested toroidal structures.
Yeah.
7 of them.
7.
And they say it's crucial for navigating this world.
That's right.
They even use this example of a red horn torus and connect it to the base chakra.
Interesting.
That's a pretty specific choice.
It is. It seems like these nested toroid elements provide a framework for organizing all the information within the vector space.
Okay.
And having those 7 layers, it's a deliberate choice for navigation and for representing data in a hierarchy.
So it's like levels of information.
Exactly. And that connection to the base chakra, it suggests that they're trying to model something deeper than just data.
What do you mean?
Maybe they're trying to capture the intuitive aspects of experience too.
Oh, wow.
Like how we feel and sense things, not just the raw information.
So they built this whole foundation, this data-filled vector space with this visual structure.
Right.
And the goal is to create a space where large language models can really thrive.
That's it.
They call it an aura,
Yes.
which is like an interactive field of information that the AI agents can perceive and react to.
It's like their version of our world.
Exactly. So we've got this abstract data that's been visualized in this really structured space.
Right.
But how do they actually turn that into a virtual reality experience?
Well, this is where the actual development tools come in.
Yeah, okay.
They use Blender to create the 3D models.
Blender, I've heard of that.
Yeah, it's a popular software for 3D modeling.
So they're using Blender to design the Tori and all those other visual elements. Yeah.
Exactly. It's like sculpting, but with data.
I like that.
Then they bring those models into Unity XR.
Unity.
Yeah, which is a platform for building interactive VR experiences.
Okay, so Unity is where they add all the interactive elements, the support for VR headsets, and the logic that connects the visuals with the data.
Exactly. They also use Unity to place lights and cameras within the virtual world.
And why is that important?
Well, it determines how the user sees and navigates the environment.
I see.
Like where they're looking, what they're focused on.
Makes sense.
It's all about creating a believable and immersive experience.
Now, the documents also mention these interactive 3D toolboards and menus.
Yes, those are really important for user interaction.
What do they do?
Imagine you're in this VR space, And you have these floating palettes in front of you.
Okay.
And with these palettes, you can select and examine the individual vectors, lines, and faces of the geometric structures.
Wow, so you can really get up close and personal with the data.
Exactly. And the tools on the palettes, they show you all the specific data linked to each visual element.
That's so cool.
It is. And the menus, they're designed to be expandable so they can add more features as the simulation evolves.
That's smart thinking ahead.
They're planning for both finite maps for each chakra and infinite maps.
Finite and infinite. What's the difference?
It's about the level of detail and the scope of the environment.
Okay.
So a finite map is like a carefully designed room.
Okay.
It's for specific interactions or analyzing certain data sets.
Got it.
An infinite map is more vast and potentially boundless.
Wow.
It uses algorithms to generate the environment based on the data patterns.
So you can have these focused explorations in the finite maps and then this sense of vastness in the infinite maps.
Exactly. It depends on what the user wants to explore.
That's incredible.
It is.
Now let's talk about actually bringing this to life in VR.
Okay.
The documents say the first step in Unity is using C#.
Yes. C# is a powerful programming language.
And they use it to set up things like Steam VR for the Vive Pro headset.
Right. That's how they enable the VR functionality.
So things like head tracking, hand tracking, and rendering the scene in 3D.
Exactly. Those are all essential for a true VR experience.
And they specifically mention using Unity's Mesh class, which is a tool for creating and manipulating the 3D geometry.
Like the toroidal shape of the environment.
Right, so that's how they build the foundation of the VR world.
Exactly. It's the framework that everything else is built upon.
But they also need a way to keep track of all that complex data.
Of course.
So they create these custom data structures in C#, vector data, and vector data manager.
Those are essential for managing the data.
What do they do?
Well, the vector data class defines how each piece of data is stored, including its position in the vector space and all its associated values.
Like a digital fingerprint.
Exactly. And then the vector data manager manages all these individual pieces of data.
So it can add, remove, search, and update information within the simulation.
That's right. It's like the control center for all the data.
Then comes the really cool part, actually connecting the data to the visuals.
Right.
So positioning the data points in the 3D space and using color to represent different attributes.
Yes, color coding is a really effective way to visualize information.
And then they build those VR tool menus so users can actually interact with this data-driven world.
It's all about giving the user the tools to explore and understand the data.
This is amazing.
It is.
Okay, let's talk about the AI agents.
All right.
They mention a mixture of experts and autogen agents.
Yes, those are the AI inhabitants of this world.
And they're all guided by this LLM controller.
The LLM controller is like the conductor of the orchestra.
It decides who does what.
Exactly. It understands the capabilities of each agent and the tasks that need to be done.
So it's like a manager or a director.
Exactly. And they mentioned Hugging GPT as an inspiration.
Hugging GPT.
Yeah, it's a system that can orchestrate different AI models to solve complex problems.
So this LLM controller, it's built with a similar goal in mind.
Right. It needs to be able to understand what needs to be done and then delegate those tasks to the appropriate agents.
So how do they actually build this LLM controller?
Well, the first step is choosing the right architecture for the large language model.
Okay.
It needs to be able to handle these specific roles.
Right.
Then they need to gather and prepare a ton of data.
What kind of data?
Or examples of how to define tasks, how to use different tools, and the knowledge that's relevant to each agent's area of expertise.
So it's like giving the LLM a crash course in everything it needs to know.
Exactly. And then they go through a fine-tuning process.
Fine-tuning?
Yeah, that's where they train the LLM to understand what needs to be done and then figure out which agent is best suited for the job.
So it's like teaching the LLM to be a good manager.
Exactly.
Okay, so now you've got this intelligent controller.
Right.
How do you get it to actually interact with the mixture of experts and the autogen agents?
Well, they set up these clear channels of communication and methods for coordination.
I see.
The LLM controller acts as the central hub.
Oh, okay.
It receives requests, breaks them down into smaller parts, and then sends those parts to the right agent.
And the agents report back to the controller when they're done?
Exactly. And then the controller can either put the pieces together or trigger further actions.
So it's like a well-oiled machine.
That's the goal.
And this isn't a one-way process, right?
No.
The controller needs to learn and adapt based on how well the agents are performing.
Absolutely. That's where the feedback loop comes in.
Tell me more about that.
Well, the LLM controller is constantly analyzing the results of the agent's work.
Okay.
And it uses that feedback to refine its strategies for defining and assigning tasks.
So it's getting smarter over time.
Exactly. It might even decide to retrain certain agents if they're not performing well enough.
That's incredible.
It's all about continuous improvement.
Now, they also talk about adding multi-agent chat to this environment.
Yes, communication is key.
So it's not just about the agents working independently. They need to be able to collaborate.
Right, and they've built in these checks and balances to ensure the quality of their work.
What do you mean?
Well, they have these task agents
Yeah.
and supervisory agents.
Task agents and supervisory agents.
Yeah, the task agents do the actual work,
Okay.
and the supervisory agents review their work to make sure it meets the standards.
So it's like a built-in quality control system.
Exactly. If a supervisory agent finds any issues, it sends the work back for revisions.
With feedback.
Yes,
Yeah.
specific feedback. So the task agent knows what to fix.
That's a really smart way to do it.
It is. And they mentioned frameworks like Autogen as tools for creating these conversable agents.
Conversable agents.
Yeah, agents that can talk to each other and work together autonomously.
So it's like a team of AI experts working on a project.
Exactly.
And they have a communication agent to keep everything running smoothly.
Right. The communication agent makes sure that messages, tasks, and feedback are all routed correctly.
So everyone's on the same page.
That's right.
Okay, so one thing that really caught my eye was this idea of running the function definer with a human in the loop.
That's an interesting approach.
How does that work?
Well, imagine you have a human expert working with the function definer AI. The AI might suggest some potential functions for a specific agent,
Okay.
and the human can give feedback, suggest changes, or even introduce completely new functions based on their real-world knowledge.
So it's a collaboration between human and AI to figure out what the agents should be able to do.
Exactly. It's about combining the best of both worlds.
I love that.
It's a really innovative approach.
So once they've defined all these functions, they need to teach the function caller and the other GPTs how to use them.
Right, the function caller needs to learn the optimal sequence of function calls to achieve a specific goal.
So it's like writing a program, but for AI.
In a way, yes. And the other GPT agents need to be trained to respond appropriately when they receive a function call.
So it's all about coordination and understanding.
Exactly.
Now, the documents provide a really concrete example.
Oh, yeah.
They talk about a project focused on aged care, dementia, mental health, personal well-being, and the medical profession.
That's a great example of how this technology can be applied in the real world.
So what does this virtual world look like?
Well, they've created a virtual care home,
Right.
a mental health monitoring center, a personal well-being hub, and a medical professional interface.
Wow, it's like a whole virtual healthcare system.
Exactly. And they have AI agents with specific roles in each of these areas.
So tell me about these agents.
Well, there's a caregiver agent
Okay,
who provides assistance and monitoring in the virtual care home.
got it.
Then there's a therapist agent who specializes in mental health and dementia support.
And a health analyst agent.
Yes, who analyzes patient data to identify any potential issues.
And a coordinator agent.
Right? Who keeps everyone connected and facilitates communication
Yeah.
between the agents and human medical professionals.
So it's like a virtual healthcare team.
Exactly.
And how would these agents actually interact with, say, a human doctor?
Well, imagine a doctor is using this system to monitor a patient in the virtual care home.
Okay.
The caregiver agent might be interacting directly with the patient while the health analyst agent is tracking their vital signs in the background. If the health analyst agent notices anything concerning, it alerts the coordinator agent.
And
The coordinator agent might notify the doctor through their interface.
so the doctor can intervene if needed.
Exactly. And the therapist agent can conduct virtual therapy sessions as well.
Wow, this is incredible.
It is. And the documents emphasize the importance of getting feedback from real-world stakeholders.
Like healthcare providers, family members, and technology partners.
Yes, their input is essential for making sure the system is practical and useful.
It's all about making sure this technology actually benefits people in the real world.
Exactly.
Okay, one last thing that I found fascinating.
Okay.
This training material simulation data.
Right.
It includes things like vocabulary content, multimedia resources, lesson plans.
It's all about teaching the AI agents.
So how does it all get integrated into this simulation?
Well, it's used in three main ways.
Okay.
First, it shapes the agent definitions.
So it defines their learning capabilities and knowledge base?
Exactly. And it's tailored to their simulated life stages.
So a young agent might have access to basic information, while an older agent would have more specialized knowledge.
Exactly.
Second, it's used by the dynamic simulation components.
Right. So the system can apply the right materials based on the agent's progress and the context of the simulation.
So it's always adjusting to the situation.
Exactly.
And third, it's integrated into the submodel integration.
Right, which contributes to the overall cognitive development of the agents.
So they're not just learning facts, they're actually developing their thinking abilities.
Exactly. It's a holistic approach to AI development.
Now, they also mention these three observers.
Yes.
The environment observer, the character environment observer, and the narrator observer.
It's like having a team of scientists watching the simulation unfold.
Exactly. So what did these observers do?
Well, the environment observer looks at the big picture.
Okay.
How the whole environment is evolving over time.
Got it.
The character environment observer focuses on the main character.
So what they're seeing, hearing, and interacting with. And the narrator observer tells the story of the main character.
Right. Their journey, their decisions, their reactions.
So these observers are collecting tons of valuable data.
They are. It's all about understanding the simulation from different perspectives.
This is truly mind-blowing.
It is.
It's incredible to see how VR, AI, and these sophisticated learning mechanisms are all coming together.
And the level of detail in these virtual worlds is just astounding.
It really shows the potential of this technology.
Absolutely could revolutionize so many fields.
It makes you think about the implications of creating these digital worlds and populating them with intelligent agents.
It does. It raises a lot of interesting questions.
Like, what new insights might we gain?
Right. What are the ethical considerations?
It's definitely something to ponder.
It is.
For anyone listening who wants to learn more, I would recommend looking into VR, AI integration, multi-agent systems, and the latest advancements in LLM control.
Those are great starting points.
Frameworks like generative agents and the research on LLM orchestration are also worth exploring.
Absolutely. There's so much happening in this field.
Thank you for guiding us through this incredible project.
My pleasure. It's been fascinating.
It has. And for our listeners, keep exploring, keep questioning, and as always, stay curious.
With your... Okay, so you know that feeling, right? Like when you really want to understand something complex, but you don't have hours to spend reading like a whole textbook or, a stack of research papers.
Yeah, definitely. I think we all get that information overload feeling sometimes.
That's exactly what we're trying to tackle here with these deep dives, right? It's about taking those complex topics and distilling them down into something digestible and insightful.
Yeah, giving you those aha moments, but without the, the mental exhaustion.
Exactly. So today we're going deep on this really ambitious idea. It's a project that's trying to create a VR AI system that can actually represent human consciousness.
Yeah, a digital twin, but not in the way you might typically think about it.
Right. It's not just mirroring your physical actions or something, but trying to capture the essence of experience.
Yeah, exactly. And what's fascinating is that they're using these kind of unconventional approaches, working with things like a nested toroidal structure.
And vector space concepts.
Right, which is this whole other way of thinking about how data is organized and how relationships are formed.
Okay, so we've got this big picture concept, but where are we getting all this info from?
So we've got a document that outlines the technical development of this system using Blender and Unity XR.
Okay, so those are the tools they're using.
Right. And then we've also got this series of discussions and prompts that explore the technical details, but also the potential applications of this technology, which gets really interesting.
And even a grant proposal context, right?
Yeah.
So we're seeing how they're trying to pitch this to potential funders.
Yeah, which gives you a good sense of, what they see as the real-world impact of this technology.
So for this deep dive, we're going to try to unpack how they're building this VR AI representation, what are the technical hurdles they're facing, and then really delve into those potential uses, particularly the stuff around aged care and mental well-being.
Yeah, because those are areas where this technology could really make a difference.
Absolutely. So, okay, let's jump in. How do you even begin to visualize something as abstract as consciousness?
Well, it seems like they started with AI image generation, specifically DALL-E 3.
Oh, wow. So using AI to help visualize AI.
Yeah, kind of meta, right? And
Right.
they created these abstract 3D illustrations, not meant to be literal blueprints, but more symbolic representations of what they were thinking.
Okay, so what did these visualizations actually look like?
Well, imagine like nested toroidal structures.
Toroidal, so like donut shapes.
Exactly. Interconnected donut shapes representing that base chakra concept.
That base chakra?
Yeah, it's often associated with, grounding and stability.
Okay, so these interconnected donuts representing the base chakra. And they were putting these inside of what?
Often they'd show them within like a translucent geodesic sphere.
Okay, a geodesic sphere, kind of like a futuristic dome.
Yeah, exactly. And then all of that contained within a cubic volume.
So you've got these layers, right? The donuts inside the sphere,
Yeah.
inside the cube.
Yeah, like a visual metaphor for the different layers of consciousness or something.
And what about the colors they were using?
Lots of radiant red hues and earthy tones, which, makes sense given that base chakra connection.
Right, grounding earthy. So, okay, we've got these AI-generated visualizations, but how do you go from these abstract images to actually building a system?
Right. So the next step involves taking those torus shapes and breaking them down into their basic geometric components. The vertices, the faces and edges.
The vertices being the points, faces, are the surfaces, and edges are the lines.
Right, exactly. And then the really interesting part is that they're tagging this geometry with data directly within the 3D model itself.
So it's not just a visual representation anymore, it's becoming a data structure.
Right, and they're using Blender's Python API to do this, which is super powerful.
So they're essentially embedding information into the shape itself.
Precisely. And it's not just like random data, it's relational data, like what you might find in a spreadsheet, but it's connected to specific points and surfaces within the 3D model.
So the shape becomes a carrier of information.
Yeah, it's a way of representing data spatially, which has some really interesting implications for how the AI can interact with it.
Right, because it's not just searching through a database anymore. It's understanding relationships based on where things are located
Yeah.
within this three-dimensional space.
Exactly.
So how do they actually visualize this data within the 3D model?
There are a few ways they talk about doing it. They could use vertex colors, so the points themselves would change color based on the data.
Okay, so different colors representing different values or categories of data.
Yeah, and they could also use materials applied to the surfaces, different textures or patterns that reflect the underlying data.
So the surface itself could become more complex based on the information it's holding.
Exactly. And then to visualize that vector space that we talked about before.
The multidimensional data map.
Yeah, they could use Blender's particle systems or the grease pencil tool to draw lines representing vectors emanating from the data points.
So it's almost like creating a three-dimensional web of relationships between all these different pieces of data.
Yeah, and it gives you a way to see how things are connected and how close or far apart they are within this multidimensional space.
Okay, so we've got the visual aspect, but how do you actually make this interactive?
Right. So for that, they're again leveraging Blender's Python API to create custom UI panels and operators.
So you're building interactive elements within the 3D environment itself.
Yeah, and you could design buttons or sliders that allow users to explore the data or manipulate the visual representation.
So it becomes a tool for understanding and interacting with this complex information.
Exactly.
And what about the AI part of this VR AI system? How does that come into play?
It sounds like they're planning to integrate machine learning by processing data outside of Blender using more specialized ML libraries.
Okay, so Blender's more for the visualization and interaction.
Right. And then the heavy lifting of the AI processing would happen elsewhere. And then the results would be fed back into Blender to update the scene dynamically.
So you're constantly getting this feedback loop between the AI processing and the visual representation.
Yeah, which allows the visualization to evolve and change as the AI learns and discovers new patterns.
Okay, so we've got Blender as our starting point, our 3D canvas.
Yeah,
But ultimately, the goal is to experience this in VR, right?
absolutely.
And Blender actually has some built-in VR scene inspection features, right?
It does. Starting with version 2.83, they've integrated the OpenXR API.
OpenXR.
Yeah, it's basically a standard that allows different VR headsets to work with software more seamlessly.
Okay, so more compatibility and less headaches.
Exactly. So if you have a VR headset, you can actually step inside your Blender creations and get a feel for the scale and the spatial relationships between different elements.
That's got to be pretty mind-blowing, seeing these abstract representations of data come to life in a 3D space that you can walk around in.
Oh, definitely. It gives you a whole new level of understanding and intuition that you wouldn't get just looking at it on a flat screen.
So you can actually experience the data spatially.
Exactly.
But Blender's VR capabilities are mainly for viewing, right?
That's right. It's more for inspection and exploration. For more advanced VR interactions, like if you wanted to grab objects, manipulate data with your hands, or create these really interactive experiences.
You need to go a bit further.
Yeah, you'd either need to do some heavy scripting in Blender's Python API, or more likely export your Blender assets to a dedicated game engine like Unity or Unreal Engine.
Okay, so those are the big players in VR development.
Exactly. They have much more robust VR development tools.
So it sounds like Blender is this great stepping stone for building the initial concept and visualizing the data. But for that full-fledged VR experience, you got to move to something like Unity.
Yeah, that's a good way to put it.
Which brings us to this idea of building the aura within Blender as a kind of a stepping stone to that full VR application.
Right.
So what does that look like in Blender? What's the setup there?
So the vision is to create 7 nested torides, each representing one of the chakras, and each having its own distinct color.
Okay, so like a rainbow of nested donuts.
Yeah, and then for each of these chakra torids, they want to set up 2 different viewing perspectives using cameras, an interior view as if you were inside the energy field, and an exterior view to see the overall structure from the outside.
So you can switch back and forth between these personal and observer perspectives.
Exactly.
That's cool. And they also talk about this concept of finite and infinite maps. What's that all about?
So that suggests that within Blender, you might have very detailed sections of the tori representing finite, specific data points.
Okay, so like high-resolution areas for specific information.
Yeah. And then other areas could use procedural textures or imported designs to give this sense of a more expansive, almost infinite data set.
So procedural textures are those patterns generated by algorithms, right?
Exactly. It allows you to create complex visual details without having to manually model every single element.
So you can create these vast landscapes of data within Blender.
Exactly.
Now, what about lighting? How would lighting play into these different views?
Lighting would be really crucial for setting the mood and highlighting the different perspectives.
Yeah, definitely lighting can make or break a VR experience.
For sure. For those personal interior views, they're thinking about using chakra-themed colored lights, to create an environment that resonates with each energy center.
So each chakra torus would have its own unique lighting scheme.
Yeah, and then the observer exterior views would use more neutral lighting so that you can really clearly see the form and structure of those nested torids.
Okay, so it's all about creating the right ambiance and making the information visually clear.
Precisely.
And earlier we were talking about those interactive 3D toolboards and menus. How would they build those in Blender?
So they're thinking about using Blender's 3D text objects to label different parts of the chakra tori.
Okay, so you'd have text floating in 3D space to provide context.
Yeah, and then for the interactive elements, they could create UI panels using simple planes with emission shaders so they look like they're glowing.
Okay, glowing menus, that sounds futuristic.
And then they can make those interactive through Python scripts, so when you click on a certain button, it triggers a specific action.
So you can select a vector or a face on the model and then get more information about it displayed on these 3D menus.
Exactly. And the idea is to have dedicated areas on the menus where they can add new functionality as the system evolves.
So it's a modular design that can grow over time.
Yeah, definitely.
So it sounds like Blender is really powerful for prototyping, for visualizing the data, and building in some basic interactivity. But when you want to go full VR with, hand tracking and all those immersive features, you need to move to a game engine.
That seems to be the consensus, yeah.
Okay, now one of the sources talked about these jumbled images. What were those all about?
Yeah, those images seem to represent the different stages of building this complex 3D model within a vector space.
So it's like seeing the evolution of this data structure as it gets more complex.
Exactly. And they get progressively more jumbled as they add more layers of data and relationships.
So the jumbledness is a visual reflection of that growing complexity.
Right, and every vertex, line, edge, face shape, and color within that model is connected to specific data in underlying tables.
So it's not just arbitrary geometry. It's all connected to the information they're trying to represent.
Exactly.
Okay, so how do those VR tool menus that we talked about earlier fit into all of this?
So the idea is that you'd be able to interact with those visual elements like the vertices and the faces through the VR tool menus.
Okay, so using the menus to manipulate the data.
Yeah, and by creating connections between them like strings or loops, you're essentially embedding new information into the model.
So you're actively building the data structure through your interactions in VR.
Exactly. And each of those actions creates a new vector with a recorded trace address in the associated data tables.
A trace address, so it's like a history log of every action that's been taken.
Right, so you can always track back and see how the data structure has evolved over time.
And how does the red torus as base chakra analogy fit into all of this?
So by anchoring the red torus as that visual representation of the base chakra, they're connecting all the data in this vector space to those early human experiences, body-mind activity observations, the environment, the observer's own narrative.
So it's a way of grounding this abstract data structure in something more relatable to human experience.
Yeah, it's like they're building a framework for a form of self-reflection where the patterns of information are inherently connected to those fundamental aspects of being human.
Okay, so we've got this really ambitious VR AI concept taking shape in Blender.
Right.
But how do they go from that to actually building it as a functioning VR program?
Yeah, so the sources outline a number of high-level steps involved in developing this as a VR program.
And they're probably going to use Unity for that, right?
Most likely, yeah. It seems like Unity is the platform of choice for this kind of project.
Okay, so what are those high-level steps?
So first up, you've got your requirements analysis, really defining what the program needs to do, what are the goals, what are the features.
Okay, so the planning phase.
Exactly. Then you've got the design phase where you're thinking about the user journey, the 3D models, the UI, the data mapping.
So sketching out the whole experience.
Yeah, and then comes the technology stack selection. So choosing the right VR platform, the programming language, the data storage solutions.
Okay, so making those big technical decisions.
Right. And then you move into the development phase where you're actually building the 3D models, writing the code for the data mapping, creating the VR tool menus, and all the logic for data embedding and the trace address system.
So this is where the rubber meets the road.
Definitely. And you also need to consider the VR interaction, how the user's going to control things, navigate the environment, and get feedback.
So making it a usable and intuitive experience.
Yeah. And of course, data integration, making sure that information can flow smoothly into and out of the VR environment.
Okay, so a lot of moving parts there. What happens after they have the initial build?
Well, then comes the testing phase. You got to make sure everything is working as expected, that it's usable, and that it performs well in VR.
Right, because VR is very demanding performance-wise.
Absolutely. And testing often involves real users, getting feedback and iterating on the design.
So it's not just developers testing it in isolation.
No, you need that real-world perspective.
And then once it's been thoroughly tested,
then you move to deployment. So optimizing the program for the chosen VR hardware and preparing it for distribution.
okay, so getting it ready for the real world.
Yeah,
Okay.
and crucially, you also need to develop user training materials and documentation to help people understand how to use the system.
Yeah. Otherwise, it's just a bunch of fancy code that nobody knows how to use.
Exactly. And finally, ongoing maintenance and updates, addressing bugs, incorporating new features, handling evolving data structures, all of that is crucial.
So it's a full-on software development lifecycle,
Mm.
but with added complexities of VR and AI integration.
Yeah, it's a big undertaking.
Now, the source material actually goes pretty deep on the how to actually program this base architecture in Unity.
Right.
So let's break that down. What are the core elements there?
Well, at the heart of it, you've got to define the data structure, that multidimensional vector space, and the associated data tables.
Okay, so building the framework for how the data is organized.
Exactly.
Yeah.
And then you need to create the 3D geometric representation, so that nested toroidal structure, and figure out how to dynamically color code it based on the data.
So making the data visually come to life.
Yeah. And developing those data mapping and manipulation tools within VR is key, as are the VR tool menus that let users interact with the data.
So giving users the tools to explore and understand the data.
Right. And then you got to bring those interaction dynamics into VR.
So things like physics and the trace address system.
Exactly. If you want realistic interactions with those shapes, you need a physics engine, and you need that address system to log every data manipulation.
Okay, and if machine intelligence is part of the design, then you got to integrate those algorithms into the VR environment as well.
Definitely. And throughout this whole process, user experience is paramount, giving clear feedback to the user, making sure the experience is intuitive.
Yeah.
And continuous testing, refinement, optimization, all of that's key to building a functional VR application, as well as good documentation.
Right. Documentation is often overlooked.
Yeah.
But it's so important for a complex project like this.
For sure.
Okay, so let's get into the nitty-gritty. What are the actual programming steps in Unity and C# to get this thing off the ground?
So you start by setting up your development environment. Install in Unity the necessary VR SDK for your headset, which in this case is likely SteamVR for the Vive Pro.
TVS.
Yeah. Then you implement the data structure using C# classes, defining how that vector data is stored and managed.
So building those foundational code structures.
Right. And then you develop that toroidal geometry programmatically using Unity's mesh class, defining the vertices and triangles that make up that shape.
So you're building that 3D donut shape through code.
Precisely.
And the source actually includes some code snippets for this, right?
It does. It shows you how to create the vector data class and the basic structure for generating a torus mesh.
So giving developers a starting point.
Yeah, but it's important to note that these are simplified examples.
Simplify. Yeah, I imagine it gets a lot more complex when you're actually building it out.
Oh, definitely.
So once you have that data structure and the geometry, what's next?
Then you need to write code to map the data to the geometry. So basically determining where each data point sits on the torus and how it's visually represented, like with color.
So connecting the information to the visual form.
Right. And then creating those VR tool menus involves using Unity's UI system and positioning those elements in the 3D world.
And how do you handle user input from the VR controllers?
That's where you use the Steam VR input system to access things like button presses and controller positions.
So you can interact with the data and the menus using your hands in VR.
Exactly. And implementing that trace address system involves logging all those user actions and data modifications.
So you're keeping track of every change.
Right. And if you're integrating machine learning, you bring in libraries like ML.NET or TensorFlow for Unity.
And then finally, you focus on optimization, testing, building, and deploying the application.
Exactly. Getting it ready for people to actually use.
Okay, so this is starting to sound pretty hardcore programming-wise.
Yeah, it definitely gets into the weeds.
So what does the really program it aspect entail? Like what's beyond those basic code snippets?
So for the torus mesh, you'd need a complete algorithm to dynamically generate the vertices, the normals, and the triangles based on parameters like the radius and number of segments.
So it's not just a static shape. You're creating it on the fly based on the data.
Exactly.
And that data structure for the vector information has to be pretty sophisticated too, right?
Absolutely. You might need multi-dimensional arrays or more complex data structures to handle the richness and the relationships within the data.
And mapping that data to the torus isn't just about placing points. It's about translating multidimensional information into 3D coordinates.
Yeah, that's the real challenge, figuring out that conversion logic to represent abstract data spatially.
So there's some heavy math and geometry involved there.
Oh, for sure.
And VR interaction that goes beyond just detecting button presses.
Definitely. You'd likely use Unity's XR toolkit to handle things like grabbing, pointing, manipulating objects with those VR controllers.
So creating a truly hands-on experience.
Yeah, and designing that VR-friendly UI is crucial, making sure it's intuitive and accessible in that immersive environment.
And integrating machine learning libraries that involves setting up data pipelines and potentially training models within Unity or connecting to external ML services.
Right. It's about building that bridge between the VR environment and the AI processing.
And then throughout all of this, it's constant optimization, debugging, documentation, version control.
Yeah, all those best practices for software development are even more important when you're dealing with something this complex.
Okay, so it's a whole ecosystem of interconnected systems working together.
Definitely.
Now, the source material specifically mentions coding for the Vive Pro.
Right.
What are some of the key considerations there?
Well, the Steam VR plugin is essential when you're working with the Vive Pro in Unity.
Steam VR again.
Yeah, it provides all the tools and integrations to interact with the Vive Pro's hardware, like the controllers and the headset.
So it's the glue that holds everything together.
Basically, and the source provides some C# code examples for checking if Steam VR is active and that basic vector data class we talked about earlier.
Okay, so more foundational code snippets.
Yeah, and they also give an outline for generating that torus mesh, again, emphasizing that the actual algorithm is quite complex.
Right, and what about handling the Vive Pro controllers themselves?
So you'd use the Steam VR input system to access the controller inputs, things like button presses and joystick movements.
So you can translate those real-world hand movements into actions within the VR environment?
Exactly.
And the source gives a basic structure for a VR controller input script that shows how to check for those button presses.
Right, but the real challenge is translating that multidimensional data into meaningful coordinates on the torus and then using those controller inputs to manipulate that representation in VR.
So again, it comes down to that bridge between the abstract data and the tangible interactions in VR.
Definitely.
Okay, let's talk about taking this to an even more detailed implementation in Unity for the Vive Pro.
Okay, so getting into the specifics.
What would that involve?
Well, you'd start by setting up your Unity project, specifically for the Vive Pro, importing the Steam VR plugin.
Setting the stage.
Yeah, then you'd create that vector data class, making sure it's serializable so you can save and load it.
Serializable so you can preserve the data structure.
Right, and then you develop a vector data manager class to manage collections of those vector data objects.
Okay, so keeping track of all those data points.
Yeah, and the dynamic torus mesh generation would require that full-blown algorithm to calculate the vertices, triangles, normals, and UVs of the torus.
So a lot of heavy geometry calculations happening behind the scenes.
And then mapping the data to the torus involves that crucial conversion logic we talked about.
Right, taking that multidimensional data and figuring out where it lives on that 3D donut shape.
Exactly.
And how about user interaction in this more detailed scenario?
So you'd lean heavily on the Steam VR interaction system, which gives you components like hand and events like hover.
So you can detect when the user's hand is near a data point in VR.
Right, and you'd write scripts to trigger visual feedback, like changing the color of the data point when it's hovered over.
So giving the user that sense of direct interaction.
Yeah, and setting up that VR camera rig and the controller game objects within the Unity editor, that's all part of the process too.
So configuring the virtual world, essentially.
And again, the key is to remember that those code snippets are just starting points. You know, they require a lot more development to create a fully functional system.
Okay, so it's a solid foundation, but there's still a lot of work to be done to flesh it out.
For sure.
Now, the source mentions adding even more functions based on those jumbled images we discussed earlier.
Right.
What kind of functions are we talking about here?
So based on those images, it seems like they want to add things like the ability to generate and visualize that 3D mesh based on the data.
So making the data visually tangible.
Yeah. And robust data management features, create, read, update, delete all those basic operations for working with data.
So you can manage the information within the system.
Right. And then VR object manipulation, being able to select, move, and rotate elements within the VR environment.
Okay, so interacting with the data spatially.
And then motion computations, maybe for different viewing angles or transitions between perspectives.
So making the experience more dynamic and cinematic.
Yeah, and then dynamic interactions where the visual elements change based on the data.
So the visualization is responding to the information in real time.
Exactly. And of course, all the interface and control elements within VR, like menus, rotation, controls all of that.
So making it a usable and navigable environment.
Definitely.
So where would these functions typically live within the Unity project?
Well, you'd probably organize them into separate classes for modularity.
So keeping the code clean and organized.
Yeah. So mesh generation and visualization would fall under a mesh generator class. Data management would be handled by a data manager. VR object manipulation would be in scripts attached to the interactable objects themselves.
Okay.
Motion computations could be part of a camera controller.
Right.
Dynamic interaction logic might live in a data point class.
Okay.
And the VR interface and controls would be managed by a UI manager.
So you've got all these different classes working together to create the overall functionality.
Right, and the source even provides some basic C# class structures as placeholders for these features.
Okay, so giving developers a blueprint to work from.
Exactly.
Let's be even more concrete.
Yeah.
How would you actually program these functionalities in Unity?
So the source outlines this base architecture to get started.
Okay, a starting point.
Yeah, so you'd have a visualization manager responsible for loading data and generating the 3D mesh.
Okay.
A draggable data point script to handle the selection and manipulation of individual data points.
Although they use mouse dragging in the example, which would have to be adapted for VR controllers.
Right, you'd need to replace that with VR input.
And then you'd have a VR interface manager to handle those VR menus.
Exactly.
And a VR camera controller to control the user's viewpoint and navigation.
Right, so you've got the core elements of the experience there.
But these are all just skeletal outlines, right?
Yeah. They'd require a lot of coding to implement the data processing, the mesh generation, the VR interactions, the UI elements.
Okay, so a lot of work ahead for those developers.
For sure.
Now, this idea of favorite or common interaction sequences, that sounds really interesting from a user experience standpoint.
Yeah, it's a great idea.
How would you set that up so users can quickly access those frequently used data points or actions?
So the concept is to let users record, store, retrieve, and pin those frequently accessed elements as interactive objects in VR.
Okay, so like bookmarks of the VR experience.
Exactly.
So how do you implement that?
Well, first you need to track user interactions, what they select, what they manipulate, what views they use.
So you're recording everything they do.
Yeah. And you could do that with a user interaction tracker class that logs each action.
Okay.
And then you need a favorites manager to store those recorded sequences.
So you're saving those sequences of actions.
Right. Probably by serializing them, converting them into a storable format.
And how would you retrieve and activate those saved sequences?
So you'd have a favorite sequences loader that loads those sequences and instantiates VR objects representing them in the world.
So you're creating visual representations of those saved actions.
Yeah. And each of those objects would have a pinned object component attached to it.
Okay, so they're like pins on a map.
And then interacting with a pinned object would trigger the replay of the associated sequence of actions.
So you can quickly jump back to a specific workflow or viewpoint.
Exactly.
And the source provides some pseudocode outlines for these classes and the logic involved.
It does, but there are also design decisions to consider, like custom classes for actions and sequences saving and loading mechanisms, placement of those pinned objects in VR.
So a lot of thought has to go into how this feature is implemented. Now let's circle back to that base chakra concept and how that data structure might integrate with large language models, LLMs.
Right. So the idea is to connect that data structure, that nested toroidal structure within a cubic vector space, to the representation of the base chakra in a traditional sense.
Okay, so grounding it in that ancient wisdom.
Yeah. The source mentions a 12 by 24 matrix table with 288 facets.
Okay, so breaking down the surface of the torus into these smaller units.
Yeah, and when you fold that into the red horn torus in the vector field, it could represent that base chakra information.
So you're mapping those traditional concepts onto this 3D geometric form.
Exactly. And that structured representation could then empower LLM computations, allowing them to interact with and interpret a spatial aura of information.
So the LLM isn't just processing text anymore, it's understanding data that's organized spatially.
Right, which opens up some really interesting possibilities.
Now, the source provides 2 pseudocode snippets related to LLM interaction.
It does.
What are those all about?
So the first snippet focuses on this life-logging conversation with hidden chakra integration.
Okay, that sounds intriguing.
Yeah, so imagine a reflective journaling mode designed for a user with early onset dementia.
Okay, so a tool for memory and reflection.
Exactly. And the key here is that the conversation framework implicitly aligns with the user's life stages and associated chakras, but without explicitly mentioning them.
So it's a subtle way of tapping into those energetic principles.
Right. The prompts are structured to encourage reflection on different periods, early years, adolescence, early adulthood, midlife, senior years.
And each of those periods is associated with a different chakra.
Exactly. So the goal is to use that chakra context to deepen the conversations, explore emotions, without the user even being aware of that underlying framework.
So it's almost like a subconscious guide for reflection.
Yeah, exactly.
That's really interesting. What about the second snippet?
So that one details a life stage agent simulation.
Okay, a simulation of human development.
Yeah, and it involves collecting all sorts of user input, age time, available learning hours, routines, experiences, efficiency, complexity, throughput, simulation, duration, focus.
Wow, a lot of variables there.
Yeah, and then it uses that input to run simulations of different life stages: baby, toddler, child, teenager, adult.
So you're simulating how people grow and develop over time.
Right, and it defines different agent interactions, self-reflection, environmental narrative, social, emotional.
Okay, so the ways these simulated agents interact with the world and themselves.
Exactly, and it defines agent capabilities at each stage, simulation parameters like token allocation.
Token allocation, so how much processing power each agent gets.
Yeah, and it even has life model variables, time allocation formulas, activity rates by stage, external influences, submodels for cognitive, social, physical, and REM sleep.
So it's a really comprehensive simulation framework driven by all these different factors.
Definitely.
But how do you actually allocate those regions of the torus facets to represent traditional base chakra information and interface that with the LLMs?
Right, so remember we were talking about that 12 by 24 matrix table and 288 facets?
Yeah, breaking down the surface of the torus.
So you could allocate specific...
All right. Welcome to The Deep Dive, the show that takes you straight to the heart of complex topics. The stuff that really matters, the stuff that's changing our world. And this time, you guys have thrown us a real curveball.
Yeah, this is some next level AI stuff, right?
Absolutely. A whole bunch of ideas, all pointing towards the future of AI. And our mission today is to make sure you can wrap your head around it all quickly and easily. So no more feeling lost in the jargon.
Yeah.
This is like your cheat sheet to understanding sophisticated AI agent teams.
You got it. It all starts with this document you shared. 12 mixture of experts, function callers, and autogen agents.pdf. Really makes you think. It's packed with these new strategies, totally innovative for building genuinely intelligent AI systems. And so what we're going to do today is like take these ideas apart, connect the dots, and show you how it all fits together, to build these incredibly realistic simulations.
Okay, so let's jump right in because this stuff it's mind-blowing. We're talking about designing intelligent AI systems. And we're going to be using some pretty crazy concepts, like mixture of experts.
Which, yeah, sounds like science fiction.
Right. Function callers, autogen agents. We're going to explore how to build an LLM control, like the brain behind it all. Then the most efficient ways to train these huge systems, how to make sure multi-agent conversations actually make sense, and even how humans stay in control. You ready for this?
I'm strapped in.
Okay, good. So one of the most fascinating things here is the idea of moving beyond those simple AI tasks. We're talking about building really rich, realistic simulations. And the document you gave us lays out this vision for like these teams of AI agents all working together. And it gets right into this key element of a central controller, this thing that guides all their actions.
Yeah, absolutely.
So it all seems to hinge on designing this LLM controller, right? And the document keeps mentioning hugging GPT. What's the connection there? What does that analogy actually tell us?
Okay, so think about it this way. Imagine you've got a big project, tons of moving parts, right? Different teams, each one with their own special skills. Now, to manage all of that chaos, you need a project manager. Someone who sees the big picture, knows what each team is good at, and can assign the right tasks to the right people at the right time.
I see.
Right? That's what a hugging GPT-like LLM controller does for AI agents. It needs to get the overall goal of the simulation, understand what each AI agent or each function can actually do, and then figure out how to delegate all the little steps to actually reach that goal.
Oh, wow.
The document really stresses that the very first step is picking the right foundation, a powerful language model architecture, something that can handle complex reasoning and give instructions, like think GPT-3.
Okay, so we're talking a seriously powerful brain at the center of all this.
Right.
Then what's the next step? How do you build out this controller?
All right, so you've got the brain power, now you got to educate it, right?
Right.
Train the central intelligence to manage the whole AI team. So what you do is you create these carefully curated, really specialized data sets. And it's not about general knowledge. This is specifically about things like defining functions. What can each AI tool or agent actually do? How do you give them instructions? What commands do you use? Which APIs? And then you also need expert knowledge specific to whatever you're simulating. And even examples of how to automatically generate content, like different types of reports. It's like creating a super specific training program for this AI project manager.
It makes total sense. It's got to know its team and how to give them orders. And then the document talks about a function definer and a function caller. They're both part of this LLM controller, right? But what's the difference? What do they each do?
This is really clever. So the function definer, part of the LLM, its job is to take a high-level request, like a simulation goal, and then translate that into concrete steps, stuff that can actually be done. It has to think in abstract terms, like, okay, what are the tasks involved here? And how can we break those down into functions that different agents can actually execute? And a really important thing it does is create API definitions, like the specific instructions to tell each agent exactly what to do.
So the definer is like the architect, figures out the what and the how,
Yeah.
and then the function caller comes in.
Okay, so the function caller, this is where the rubber meets the road. It looks at what's happening in the simulation right now, in this moment, and decides which API calls to make or which expert agent needs to jump in. It's making real-time decisions on the fly based on what the simulation needs at that exact second.
Got it. So we've got this central LLM, right, that can design the tasks and send them to the right AI specialist. Now, how does it work with all those other things we mentioned, like mixture of experts and autogen agents?
Oh, this is where it gets really interesting. So the mixture of experts, the idea is you have a whole bunch of different AI agents, each one with like deep knowledge in a specific area. There are the specialists. And autogen agents, these guys are the content creators. They generate reports, write communications, anything you need to, produce content for the simulation.
So if the LLM controller is the project manager, the mixture of experts are all the different departments, and autogen agents are the content team.
Perfect analogy. And for it all to work smoothly, you need everyone speaking the same language, right? Clear communication. The LLM controller has to be able to give instructions to these agents and get responses back in a way that everyone understands. So maybe it's predefined commands, a specific request format, or those API calls we talked about. The point is everyone's on the same page.
So the controller asks for something using this shared language. The expert or autogen agent does their thing and sends back the result. But how does the controller make sure everything stays on track, that the whole process keeps moving forward?
The LLM controller, it's like the conductor of the orchestra, right? It manages all the tasks. When it gets a request, could be from a user interacting with the simulation or from within the simulation itself, it analyzes it, breaks it down into smaller functions, and then assigns those functions to the best expert or autogen agent for the job.
So it's like an air traffic controller, but for tasks.
Exactly. And the document emphasizes that feedback is super important. Once an agent completes a task, they report back to the LLM controller. And that feedback is gold because the controller learns from it. It figures out what worked, what didn't, and uses that to improve how it delegates tasks in the future.
So it's not just a one-way street. The agents are actually helping the controller get smarter. Now, the document goes on to talk about implementing FastMO to train our mixture of experts LLMs. We've talked about mixture of experts, but what is FastMO and why is it so important for training?
Okay, so training these LLMs, especially with the mixture of experts architecture, requires a ridiculous amount of computing power.
I can imagine.
FastMO is like this turbocharged system built specifically to make that training process way more efficient. It's built on PyTorch, and it's designed for these distributed computing environments where you have multiple GPUs all working together.
Okay, so we're talking serious parallel processing power.
Yeah, like a supercomputer. Training these models often needs a whole cluster of machines all linked up. And FastMO manages all of that complexity. It distributes the model itself and the training data across all these resources. There are several key steps the document lays out for using FastMO. First, of course, you have to set up that distributed computing environment, and then you install PyTorch and the FastMO library.
Right, you need the infrastructure in place before you can do anything. And then how does FastMO actually work with the model's architecture?
Okay, so you have to design your LLM to specifically include what are called MOE layers. These layers are basically containers for multiple expert neural networks. And there's this really important gating mechanism that decides which expert or which combination of experts should handle each piece of data. FastMO gives you the tools to integrate these MOE layers into those typical LLM architectures, like the transformer networks.
So instead of one giant neural network trying to do everything, you have all these specialists, and the data gets routed to the right expert. That's got to be more efficient, right?
Way more efficient. And FastMO takes it even further. It helps you figure out how to spread those experts across all your hardware, how that gating mechanism works, and how to prepare your training data for this distributed setup. It even has optimized code specifically for those NVIDIA GPUs, what they call CUDA kernels, and it handles all the communication between the different GPUs, which is a huge deal for making distributed training actually work well.
Okay, so it takes care of a lot of the heavy lifting, the technical stuff behind training these MOE models. And the document also mentions setting up a feedback loop during training. How does that work with FastMO?
So as you're training, you need to keep an eye on how each individual expert within that mixture of experts is doing. Are some being used way more than others? Are any consistently underperforming? This feedback loop lets you tweak things as you go. You might rebalance the data load or fine-tune that gating mechanism to make sure data is being sent to the right expert. This constant evaluation and adjustment is crucial for getting the best performance out of your model.
So it's not just setting it and forgetting it. You're actively managing and optimizing the whole time.
Right.
And then, once this massive model is trained, what are the big things you need to think about when you're saving it and deploying it?
Deploying an OE model, it's like a whole other challenge, honestly. The system where you're actually going to be using the trained model, it has to be able to handle this distributed nature, the dynamic routing of data. You have to think about how all those parameters, the model's learned knowledge, are stored and loaded efficiently, and how the gating mechanism will work in a live setting where you need low latency and high throughput.
This is getting pretty intense. Okay, let's move on to another interesting topic. Multi-agent chat with checks and balances. In a simulation, with all these AI agents talking to each other, how do you make sure they're doing their jobs correctly?
That's a really important question when you're building any kind of complex system with multiple agents. You need safeguards, ways to guarantee quality and prevent errors from, spiraling out of control. The document describes this system with different agent roles. First, you've got your task agents. These are the ones doing the actual work, carrying out specific tasks within the simulation.
Uh-huh.
Then you have a supervisory agent, it's basically the manager, oversees the task agents, reviews their work, and gives feedback. And finally, there's a communication agent. It's like the messenger, making sure information flows smoothly between everyone.
So you're building a team with different roles and a layer of management for quality control. Can you break down a typical workflow in this kind of setup?
Okay, so it usually starts with a specific task being assigned to one or more of the task agents. They do their work, and then they submit it through the communication agent to the supervisory agent for review. The supervisory agent checks it against the quality standards, the requirements of the simulation. If it's good, it's approved. But if there are problems, the supervisory agent sends feedback back to the task agent and tells them to fix it.
So there's a built-in revision process.
Exactly.
What about those checks and balances the document mentions? Is that separate from the supervisory role?
Those are like extra layers of protection. Maybe you do random audits of the task agent's work, or you set up a peer review system where other expert agents double-check each other's results. You could even have a scoring system that tracks each agent's quality over time. It's all about accountability and spotting areas for improvement. These checks and balances are a safety net, catching those errors that might slip past a single supervisory agent.
Very thorough. Now, the document also talks about having a human in the loop, specifically for defining the functions these agents are going to perform.
Oh.
Why is it so important to have a human involved at this stage?
Well, even though our LLM controller is really good at figuring out what agents can do, human expertise is still priceless, especially in the early stages. The document suggests this kind of collaborative process where a human expert works directly with the function definer part of the LLM. It's all about bringing in that human domain, knowledge, real-world experience, common sense, the stuff an LLM might miss.
So the human brings the practical, real-world understanding. How does this collaboration work in practice?
They might start with, brainstorming sessions, workshops, where the human expert and the function definer LLM work together to figure out what each agent needs to do in the simulation. They identify the specific functions, the actions each agent needs to be capable of, and then they can even bring in the individual agents themselves to get their feedback on the proposed functions.
So it's a three-way collaboration, the human, the LLM, and the agents themselves. And once they've got all these functions defined, what happens next?
Once they've hammered out those functions, the next step is to train the function caller, the part of the LLM that decides which functions to use when.
Right.
And at the same time, you're training all the other GPT-powered agents on how to respond when the function caller calls on them. But even after that initial setup, human oversight is still really important. The document stresses that, monitoring the agent's performance, making sure they're interacting correctly, adapting those functions as the simulation changes.
That makes sense. You need that ongoing human check to keep things on track. Now let's talk about the environments these agents are operating in. The document talks about defining explicit scenarios and environments. Why is that so important?
Defining clear scenarios and environments is like the foundation for making all those agent interactions actually meaningful. Without context, their behavior doesn't make sense. It's just abstract actions. But if you ground them in a realistic setting, then you can test their problem solving, their ability to interact, their effectiveness at achieving goals in a specific situation. It gives you a way to analyze their strengths and weaknesses.
And the document has this great example, the virtual integrated care system for aged care and dementia. Can you walk us through that?
Yeah, so this scenario lays out this virtual environment, really detailed, for simulating all these different aspects of aged care. It has several different parts. A virtual care home, which simulates a residential care facility. You can interact with virtual patients there.
Oh.
Then there's a mental health monitoring center for data analysis and virtual consultations. And there's a personal well-being hub with memory games, social interaction features, health education resources. And then there's a medical professional interface, so human healthcare providers can monitor the simulation, give guidance, and intervene when necessary.
Like a digital twin of the whole aged care ecosystem. What roles do the AI agents play in this virtual world?
Okay, so within the simulation, you've got a bunch of specialized AI agents, each with their own job. The caregiver agent provides daily assistance to virtual residents, checks on their health, helps them socialize, suggests activities.
Yeah.
Then there's the therapist agent, focused on mental health and dementia therapy, cognitive exercises, emotional support. And the health analyst agent is constantly analyzing patient data, looking for trends, potential problems, generating alerts for the human medical staff. And then you've got the coordinator agent, which is like the glue that holds it all together, making
Yeah.
sure everyone's communicating, all the AI agents and the human professionals, so care is coordinated and integrated.
So it's like a whole network of AI agents all working together in this virtual care home. How do they actually interact with each other and with the virtual patients?
The interactions are designed to mirror real-world care as closely as possible. So, for example, the caregiver agent might help a virtual patient get ready in the morning while also checking their vital signs and talking to them. The therapist agent might conduct a cognitive training session tailored to that specific virtual resident.
Hmm.
The health analyst agent is always working in the background, crunching all this data from the agents and the patients, looking for red flags.
Hmm.
And if the health analyst agent spots a potential problem, the coordinator agent makes sure the human medical staff gets that information right away through that medical professional interface
Wow.
so they can intervene quickly.
So it's constantly adapting, responding, different agents sharing information within this virtual world.
Yeah.
And the document mentions this aura of intelligence concept. What does that mean exactly?
Right. The aura of intelligence, it seems to be this guiding principle for creating AI that's not just smart, but also empathetic and supportive. In the context of the aged care simulation, it's about the overall level of intelligence and personalized care that the agents provide.
Hmm.
The goal is for the virtual patients to have a really positive experience. And there's actually another document you shared, Aura of Intelligence, a guide for dementia sufferers, which goes even deeper into this. It describes it as a kind of personalized digital companion, offering memory aids, decision support, and tailored engagement. And the really interesting thing here is the shift from AI that's just task-oriented to AI that's truly empathetic. It's not just answering questions, but understanding emotional cues, offering help proactively based on each individual's needs and preferences.
Wow.
It's about really understanding the nuances of dementia.
So it's like the virtual environment is the stage, and aura of intelligence is the guiding philosophy for how the AI agents act on that stage. Now, another interesting point from the moextended.pdf is this idea of training material simulation. How do they incorporate predefined educational content into this?
This part is about actually teaching the AI agents, giving them structured learning experiences within the simulation.
Uh-huh.
You can feed them predefined educational content tailored to different stages of a simulated life. It could be vocabulary for a certain age group, subject-specific stuff like math or history, multimedia resources like images or audio, even structured lesson plans with learning goals and
That's
assessments.
like giving them a curriculum, like they're students in a virtual school.
Exactly. By exposing them to this material, you can shape their development, influence how they act in the simulation, and improve their understanding of different concepts and areas of knowledge. And the document even has examples of how this content could be organized for different simulated life stages, from, very basic sensory inputs for infants all the way to really specialized knowledge for adults.
Fascinating. You're not just simulating interaction, you're influencing how the agents actually learn and grow within the simulation.
Right.
And lastly, the document mentions incorporating observers into the simulation. What are these observers for? What do they do?
Observers add another layer of analysis, helping us understand what's happening in the simulation. There are three types mentioned: an environment observer, a character environment observer, and a narrator observer. The environment observer basically gives us a high-level overview of what's going on in the whole virtual world.
Mm-hmm.
The character environment observer zooms in on the main character, focuses on what they're experiencing directly, and the narrator observer is more interpretive. It watches what the main character does and tries to tell us what's going on in their head, how they're reacting to things.
So they're providing different perspectives on the same events.
Exactly.
How does that help us understand the simulation better?
Because they give us information that we might miss if we just looked at the agents and patients interacting. The environment observer gives us the big picture. The character environment observer shows us the simulation through the eyes of the main character. And the narrator observer adds this layer of interpretation, trying to understand the character's internal state.
I see.
This deeper understanding can help us figure out if the simulation is realistic, if it's working the way it should, and even if there are ethical implications we need to think about.
Wow, this has been a really deep dive into a really complex but really exciting field. Let's sum up some of the key things we've learned. So we talked about this amazing architectural approach to building AI simulations. It's all about having an intelligent LLM controller at the center, managing a team of specialized mixture of experts and autogen agents, which are basically the content creators. We got into the technical details of how to train these huge models using Fastmo. And we talked about how important quality control is, making sure those multi-agent interactions are reliable, and how human expertise is still essential, especially when you're defining what the AI agents can do. Then we looked at how crucial it is to create these very specific scenarios and environments, like that virtual integrated care system for aged care and dementia, to give the agents a realistic setting to operate in. And we finished up with this idea of using predefined training materials to shape how the agents develop, and how adding observers can give us even more insight into what's happening in the simulation.
You nailed it. That's a great summary. The thing that really stands out to me is how interconnected everything is. It's not about creating individual AI agents. It's about building a whole ecosystem where they can work together, learn from each other, and contribute to these really sophisticated simulations that can teach us about complex systems and human behavior.
Absolutely. It really shows how AI can go beyond just, automating tasks. It can help us understand, model, and even solve some of the biggest challenges we face. And it really makes you think when you consider how powerful these simulation technologies could become. Think about education, science, urban planning, even trying to understand things like the global economy or climate change. What are the limits, do you think, on what we could eventually simulate?
That is a huge question. The possibilities seem almost endless, especially as AI keeps getting better. But with that power comes a lot of responsibility. We have to think about how to develop and use these technologies ethically.
Definitely food for thought. Well, you've given us an amazing overview of this cutting-edge technology. To everyone listening, if you want to explore this more, check out the source material we talked about, and keep thinking about the potential of these AI simulations and what they might mean for our future. If you have any questions or thoughts, feel free to reach out. Thanks for joining us on this deep dive.